Hello, my name is Donald Hume, and I'm from the University of Denver Center for Orthopedic Biomechanics. This is a podium presentation from ORS 2016 titled The Strength Response of a Specimen-Specific Multiscale Musculoskeletal Model of the Healthy Human Knee. There were no conflicts of interest to disclose, and we wanted to acknowledge the funding for this project from the NIH. And as part of that funding, we've actually made available freely online a large amount of imaging, experimental, and modeling data. And we're quite excited about this, and if you're interested in it, please feel free to check it out. The evaluation of dynamics of the human body is an incredibly important tool for researchers and clinicians. We record motion, force plate data, and electromyography of subjects performing complex tasks we wish to study. Musculoskeletal modeling uses these inputs to predict muscle forces and joint loads, quantities which are difficult to measure in vivo. These models use rigid body motion and generic geometry of the musculature and bones. Specifically at the knee, we often see a simplified joint representation, either as a hinged knee or using prescribed knee kinematics based on cadaveric measurements. The current state of the art is to take muscle forces and joint loads obtained from OpenSim and use these as inputs to a more complex finite element representation of the joint. Finite element models incorporate detailed soft tissue and bony geometry and allow for estimation of stress and strain in the joint. But there is a clear disconnect here. That is, we do not measure the interaction between muscle forces and joint level soft tissue response. So the goal of our work is to build a musculoskeletal FE model that maintains complex bone and soft tissue geometry, has a healthy joint laxity response to force and motion, an accurate representation of tendon and muscle, and when combined can be used for dynamic musculoskeletal modeling, all while being validated at multiple scales with in vivo and in vitro data. The aim of this work is to demonstrate how incorporating a detailed representation of the knee with a calibrated joint laxity response affects muscle moment arms and maximum isometric extension and flexion moment. Well, why should we care about this? Well, including the interaction between muscle and joint level soft tissue reveals the relationship between joint and muscle mechanics and allows for a more realistic representation of joint and muscle pathology and investigation of treatment. So now a bit of background on the creation of the lower extremity model. Bone and cartilage were segmented and meshed from MRI images. A ligament representation was implemented which included collaterals, cruciates, and a joint capsule representation. Joint laxity calibration was performed using load cell and motion data collected during an experimental loading of a knee specimen. Optimization was performed on ligament parameters including stiffness, slack length, and attachment location to calibrate the soft tissue response of the joint to force and motion. Validation of ligament and patellar response was performed using a dynamic simulation of in vitro knee mechanics during gait. The PF ligament attachment points were calibrated to match quad forces and PF kinematics in experimental data. Building on work completed previously, a complex muscle representation was implemented in the FE model. This included 10 muscles, 4 quadriceps, 4 hamstrings, and 2 gastrocs. Multifiber representations for the vastus medialis and lateralis were implemented to better facilitate force generation over the entire range of motion. The quadriceps utilize centroid paths segmented from the visible human male, and the model uses a 3-element hill-type muscle model with muscle parameters from literature being calibrated such that the strength response match subject data. Insertion and origin positions from literature were also calibrated to match moment arm data reported by Buford. To illustrate the difference between a joint laxity response and no joint laxity response, we performed 3 simulations using the musculoskeletal FE model. An unloaded knee extension, which would be used to calibrate moment arms with results from Buford, a maximum isometric flexion task with the knee angles ranging from 5 to 120 degrees of knee flexion, a maximum isometric extension task. The maximum isometric strength tasks were used to compare changes in moment arm geometry, and the results would be compared to experimental data to calibrate the strength response of the model. We performed our own maximum isometric knee strength testing on 12 healthy subjects, anthropometrics listed below. Each subject performed a maximum isometric flexion and extension task with the hip fixed at 60 and knee angles ranging from 15 to 115 degrees of flexion. This data would be used as a standard of maximum isometric knee strength for model muscle calibration. Now on to the results. Let's begin with a plot of the results reported by Buford. This figure shows moment arm as a function of knee angle, with the gray region representing plus or minus 1 standard deviation. If you're not familiar with the experiment performed by Buford, he fixed the femur and performed an unloaded knee extension, while measuring the moment arm of 13 muscles using the tendon excursion method. We simulated that same unloaded knee extension, and you can see that the results compare well with those reported by Buford. We also calculated the moment arms of our muscles during the maximum isometric flexion and extension tasks. You can see that a joint laxity response allows for a change in both magnitude and shape of the moment arm curve during this task. Now onto the results for the maximum isometric strength. Let's begin again with the experimental data. The figure shows maximum isometric knee moment as a function of knee angle, with extension being positive and flexion being negative. The gray region represents plus or minus 1 standard deviation on the data we collected on our 12 healthy subjects. At this point, we actually performed one additional simulation. Again, our goal was to show the difference between joint laxity and no joint laxity, and so we performed a maximum isometric flexion and extension task using kinematics obtained from our unloaded knee extension. So in other words, we simplified our model and removed the joint laxity effect. Those results are seen here. And then finally the results of our musculoskeletal FE model with laxity represented. You can see that the laxity response causes a decrease in the maximum isometric extension moment and an increase in the flexion moment. The changes we see here are a function of not only the moment arm changes seen previously, but also a change of the muscle tendon length and relative TF alignment of the joint. So in summary, we created a musculoskeletal FE model that was built with a calibrated laxity response. Hopefully we demonstrated that the soft tissue response at the joint will in fact have an impact on force generating characteristics of the muscles. And the current state of the art is to calculate muscle forces and joint loads in OpenSim and use these as input to a more complex FE model. The limitation here is that we do not account for the interaction between muscle force and soft tissue response at the joint. Muscle force prediction during a dynamic task with a musculoskeletal FE model will allow for improved model realism moving forward. We will be able to iteratively update muscle forces using new joint angles, muscle tendon lengths, and moment arms. We will be able to analyze stress and strain in ligaments, tendon, and cartilage and drive kinematics with radiography if we choose. This new method will allow us to consider changes in soft tissue response at the joint given different pathologies, such as a meniscal tear, ligament rupture, and even implant evaluation. Thank you.